Hi everyone, welcome to my talk, which will be about Qdrant, which is a vector search engine written in Rust. So don't worry if you know nothing about vector search engine in general, we'll go through the basics together. So first, who am I? So now you know I'm Arnaud. I'm a software engineer and a full-time contributor on the Qdrant project. My two favorite things are open source software and Rust, so I'm very grateful to be able to work on the Qdrant project. I have myself a bunch of open source projects that I maintain. You can find those on my GitHub profile. And I also have a blog where I write about my projects and about Rust. And I enjoy particularly to write about the performance aspects of developing in Rust. Cool. So the agenda. Of course, we're going to talk about Qdrant, but this won't be a sales pitch. I will give you a general introduction to vector search engines, so that you can transfer what you learned today in with other products. Everything's okay. We'll go over a couple of use cases for the technology, because good technology without good use cases, not really interesting. We'll peek under the hood, see how it works internally, and by doing so, we'll hopefully see why Rust is a very good fit for the job. Okay, so what is Qdrant? Now you know it's an open source vector search engine, fully written in Rust, and we do embrace the Rust ecosystem. That is, we have a lot of dependencies. We do suffer from time to time from long build times, but that comes with the tooling, I would say. Concretely, you interact with Qdrant via an HTTP, JSON API, or gRPC if you prefer. We have for that 3 official clients, Python, Rust, and Go. It is possible to deploy Qdrant in a distributed setup, which is nice for scaling. But if you do not like to handle the operations yourself, you can use our software as a service. We have a cloud offering so that we'll run and manage a Qdrant cluster for you. To understand what Qdrant does, it's good to have a look at the evolution of search for the past years. Traditionally, search has been about having an exact match on a text keyword. If not exact, then maybe relying on a list of synonyms, or if maybe a fuzzy match with something like an edit distance to have a better match. However, if we look at the internet, we have a growing amount of unstructured data. We have collections of text files, images, videos, audio files, and we have trouble making sense of all this data. Also, if you use the internet, I'm sure you've noticed that all websites now do recommendation. You go on e-commerce websites, they offer recommendation for products. So you want to watch a video, here you go, you should watch this video, you should listen to this podcast, and so on. And this changing trend can be described under the umbrella of similarity search. This is what we're going to have a look at. The easiest example of similarity search is the Google Lens project, which perform reverse image search. Concretely, you take a photo, you upload it on the Google Lens service, and it will first find pictures that are matching visually your photo, but it also give you additional metadata. So in that case, I take a picture, and Google tell me this picture, this is this flower. So the first time I used this service, I was really blown away, and I was wondering, how is it working? And I don't know, if you think about it yourself, how would you implement something like that? Would you maybe do pixel comparison, which sounds a bit difficult, or maybe rely on some complicated edge detection computer vision library? But I'm not sure this would be as general as what vector search proposes. This was an example for similarity search with a picture, but you can, of course, apply a similarity search to text, and it's called neural search. Here we have an example. We take a subset of Wikipedia, and we're going to query it with what is the capital of the United States. On the left-hand side, we have a classical lexical search, PM25, that relies on keywords, and on the right-hand side, we have a new neural search approach. And we can see that for the classic approach, The first result is the capital punishment has existed in the United States since then. I guess there's a date. And the second and third results are not correct either. So it seems that the lexical search has removed the stop words in the query and has really focused on a couple of keywords. The problem here is that keywords, I mean, words have different meanings depending on the context. So this really tripped the lexical search approach. Whereas on the right-hand side, we have the neural search. And here we see the top hit is what we want, it's Washington, D.C. The neural search has been able to really understand the query in its entirety according to the context. So neural search is pretty good at answering long queries. Similarity search is done by using so-called similarity models. Those models, they are trained via machine learning. There are a lot of models online that you can take off the shelf, websites like Hugging Face, but you have to be careful. A specific model will not necessarily fit your domain. When you pick a model, you have to make sure that it has been trained on data that is really close to what you're doing. The alternative is otherwise to build the model yourself. And if the model is large, it can get pretty expensive. For the remaining of this presentation, I assume that we have a working model. Otherwise, those are more machine learning concerned. What is a model anyway? So concretely, a model takes a complex object, let's say a picture, MP3 file, and then it's going to reduce it into a vector. And those vectors are called in the ML jargon, they're called embeddings. And now the secret sauce for those similarity models, maybe a very good information to remember from this talk, is that similar inputs are vectors that are close to each other in space. Here we have an example. We have a query and a document that we both encode using a neural encoder. We have then a query embedding and a document embedding. So those are two vectors. And we are able to compare those vectors by relying on the cosine similarity metric. So cosine similarity, it relies on the angle that is formed between those two vectors to compare them. That's the magic. Here is the first, let's say, checkpoint, a little executive summary about vector search engine. Now we know that those vector search engine, they enable similarity search use cases, like semantic search for text, similar images, recommendation systems. They mostly have two roles. They perform storage, that is, they persist durably vector embeddings, and they enable a search use case, that is finding vectors that are the most similar to an input vector. And obviously, the whole game here is to do those things very efficiently. We're going to make this very concretely with an example that is taken from a blog. Here, the goal is not to look at every line because we don't need all of those. We're just going to understand what's going on. We're going to use here the Python driver because this is what most data scientists are using. Here in this first snippet, I picked it. I wanted you to really understand that it's really that easy to load a model in Python using the sentence transformer package. Just one line, model equals sentence transformer, give a name. Now you have a model to work with. Second step is to create a Qdrant collection. So the collection is the abstraction that is holding your vectors. That's what you're going to work with. On top of doing the networking configuration, we create the collection by giving it a name. And then the most important is the vector configuration. We have to inform Qdrant of the dimension of our vectors. Here, the size is 384. It's absolutely not a random number. This number comes from the model. The model produces vectors that have this size, so they must be an exact match. And then we also tell Qdrant what is the distance metric we're going to use. Previously, we've seen the cosine similarity. Here we use the dot product, so it's possible to pick whichever distance we want. Once we've created our collection, we can ingest data into it. And the interesting bit is to perform a search. Here we have a search term, and we want to search our collection with that term. And we cannot just send that search term Earth observation to Qdrant. Qdrant doesn't understand strings, it understands embedding. This means you have to encode the search term as well. Then you can send it via this search function on the driver. So the point that I want to hammer here is that the model is necessary for ingesting data, but it's also required for at search time. So this maybe will put some constraint on your architecture. Otherwise, you'll have to maybe pre-compute the vectors ahead of time. Something specific about Qdrant, we are not dealing only with vector, but now you have more interesting use cases. You can attach additional data to your vector. Here on the right-hand side, we have an example where we're going to insert 3 points into a collection we were mentioning. A point is something that has an ID, a vector, and a payload. And the payload is just a JSON object. You can attach additional data that can be used then for filtering. So if you think about it, not only you can ask the question, please find a restaurant that is similar to this restaurant, but you can say, and please make sure that it is within a radius of I don't know, 500 meters from my place. This is pretty neat. We support different type of payload. Here I mentioned geo-coordinates, but we have, of course, text, numbers, and so on. All right, let's dig a bit deeper now. How would you implement vector search yourself? I always ask myself this when I use a tool. And the way you could do it is simply you use a SQL database. You create a table, and for instance, if we have vectors with 4 dimensions, we just have 4 columns. W, X, Y, Z. And you just insert all your vectors in there, and you're done. Now we have a search. What do? We have an input vector coming in. We need to compute the similarity between our vector and each vector in our storage. So we go through the table, and on our way, we're going to make sure to remember which of those vectors has the highest similarity. Then we have it, we can return it to the user. I guess you understood, we just perform the full table scan. This kind of approach can work fine if you have a small data set, I would say between 10,000 vectors to 100,000 vectors, depending on the size, on the dimension of the vector. But quickly, you're going to run into problems here. Generally, if you are doing a database business and you are running into full table scan, you're going to think, I know, I need an index. And we need an index here as well. But we need a special index. So little reminder here, an index is really a structure that is optimized for reads that we're going to build ahead of time to support our queries. Unfortunately, you cannot just use traditional indexes here, like slapping a posting list or a B tree. Fortunately, there are already specialized indexes for vectors. That's not something new. We have the entire geospatial work there. You have indexes like the KD trees, which enable you to do geo-coordinate queries. Once you have those indices, you're able to perform what is called a k-nearest neighbors. That is a search that finds the nearest neighbor to a point. However, you have a problem with those, is that those space partitioning techniques, they are too expensive in high dimension. This is known as the curse of dimensionality in the literature. Basically, all the tools we have regarding algorithm and data structure, they start to break apart as the number of dimensions increase. But we need to handle very large dimensions, so how are we going to go about it? As usual, one way to fix your problem is to relax the constraints. And this is what we're going to do with something called ANN search. So ANN stands for approximate nearest neighbors. And here the constraint we relax is we're not going to ask for the exact precise result. We're going to say, I'm okay if this is an approximate result. So the trade-off here that you're performing is really precision versus speed. Here I have a a screenshot that shows you various algorithms, because this is really an active area of academic research. A lot of people are working on this. And you can see on the bottom, it's the precision. I don't know if you can read. You see 1/2, so you have 50% and goes 90%, 99%, 99.9. So you see, we're talking about approximate result, but this is really well over 99%. It's highly dependent on your data set, but this is what kind of precision we're talking about. There are many good algorithms there. Globally, there are 3 categories. You have the tree-based ones, the hashes, and the graphs. For Qdrant, we decided to go with a graph-based algorithm because it's more flexible, and the one we picked has pretty good performance. It's the HNSW one. Now we're going to dig a bit into HNSW. HNSW stands for Hierarchical, Navigable, Small Words. I'll try to explain it properly. Basically, you have different layers of proximity graphs. So proximity graph is if you are close to each other on the graph, means you are close to each other according to a metric function. The trick here is that we're going to separate the links according to their length scale into different layers. So on top, we have the long links, middle links. At the bottom, we have the short links. This way, we're able to use our graph as a skip list. If you don't remember skip list, you are jumping to a more dense representation as you go down. If you want like a metaphor, let's say you want to travel to the other side of the planet, first you're going to take a plane, that's your layer 2, then maybe you're going to take a train, that's your layer 1, and then maybe you're going to take a taxi for your layer 0. Yeah, that's how you think about it. Then you're going to go through this graph performing a greedy search. You're going to take your query, you're going to find the point that is the most similar to your query on the layer 2. Then once you have the point that is the most similar, you're going to go down 1 layer and repeat this until you reach layer 0, and hopefully you find the best result. So this process is approximate because we do not, we encode only at most m friends, that is m nearest neighbor per vector. And also at each layer, we don't perform an exhaustive search. We only look at EF search node per layer. Of course, you can make M bigger, but it's going to make your graph much more complicated to build. And if you make EF search bigger, means that your search time are going to be longer. If you are very interested in this topic, I can recommend reading the paper from 2018. It's very nice. To talk a bit about Rust, this part is quite expensive, and we use Rayon to make it faster. There is an implementation of HNSW, but we could not use it for 2 reasons. First, the reference implementation is in C++, and also we need to support payload filters. Remember, we do not only look for the closest point, we also want to make sure that they match a specific criteria. This enables many interesting use cases. If you think about it, there are 2 approaches to do filtering on HNSW. You could do what is called post-filtering. First, you go through your index, you find all the similar points, and then from this result set, you will filter them. Now, this has a problem because it forces you to overfetch from your index and then hope that you'll have enough points when performing the filters. The other approach is to do pre-filtering. So first, you're going to go through some kind of index to find all the points that are matching a specific filter. Once you have this result set, you will check which are the ones that are the closest to your input query. So in that case, you do not even use your HNSW index, which is a bit suboptimal, let's say. Those 2 approaches were not good enough for us. So we have a third approach where we actually enrich our graph with additional links regarding the payload of the indexed points. This approach enables us to perform the search in a single pass, called like single stage search. And that's really one of the key points that makes Qdrant fast. If you are interested in the details of this approach, I can recommend having a look at this blog article. All right, let's go back to the distance metrics. So by now, you should understand that this is a very, very common operation at runtime. We do it a lot during indexing when building this, those layers, and also at search time when going through the graph. We have several similarity metrics available depending on the encoder. That's kind of dependent on your model. That is, internally, we've decided to use a trait to abstract away the concrete metric. This enables us to really split the metric implementation from the indexing and the search. And this way, we can add new metrics without breaking the whole code base. Here, I've simplified a bit the metric trait. The most important function here is the similarity one, which takes as input 2 slices of F32s and gives you, as a result, a single F32. And here the comment is really clear: greater the value, the closer the vector. Let's pretend we implementing our vector search engine and we want to implement dot product that we were using in the previous example. So the dot product, a quick reminder from high school maybe. When you have 2 vectors, you want to compute the dot product. You can do it by summing the pairwise multiplications. Yeah, that's a simple definition. And here we're able to do it using the nice iterator from Rust. First, we take the first vector. We're going to zip it with the second vector. And as we go down through it, we perform the multiplication. And at the end, we're going to reduce it with a sum. So I really like this implementation. It's a single line. And it will also show that Rust can be a functional language as well. So I called it naive.product, but I think it's pretty decent. Let's say we ship this and we start doing a lot of search or indexing on it. And let's have a look at how the system responds. You're doing a lot of search. You want to see what's going on your CPU. You start profiling it, and then you find out that 70% of your CPU time is spent into the sum function of the iterator, let's say, infrastructure. If you can see, we can go through the stack, bottom to top. Start at the bottom from our Tokyo runtime. Then we're going to go up our vector storage abstraction until we reach something called HNSW index graph layers. That should ring a bell if you remember what we talked about. And then this is the point where we're going to try to find the points that are more similar to each other by calling the dot similarity routine function that is basically our implementation. So you see this, and so you wonder, is it slow? Well, to be honest, you don't know if it's slow. To know if it's slow, you would need a different implementation to compare it with, right? For now, you just know that this implementation is CPU bound and that it is a bottleneck. And this means that if you remove the bottleneck, you most likely have huge gains. And of course, this is what we did. To do so, we used SIMD. So SIMD stands for single instruction, multiple data. This is those are specific instructions that your CPU can use. And what they do is they apply a single operation to multiple data simultaneously. They're pretty magical in that sense. Those instructions are very specific to on a per microarchitecture basis. You have the x86. For x86, you have the old SSE family, the old AVX, with the latest one being AVX 512. For ARM, you have Neon. Those instructions, they all have different width. The more modern instructions have larger width, which tell you how much data you can stick into it. And as those instructions get better, they get new functions to combine results. There are 2 ways to use SIMD. Either you hand code the intrinsic yourself, or you rely on auto-vectorization from a compiler. To be honest, if you really want to make sure you're using SIMD, you have to encode it. I would never rely on auto-vectorization. Broadly speaking, there are two classes of SIMD instructions. You have the horizontal one, which take a single vector and apply an operation to it to reduce it. So in that example, this is a horizontal add. We add all the elements. Or you have the vertical operations, which take two vectors and apply the operation on a pairwise fashion, and at the end you get a vector. In this example is a vertical add. Now we want to use those, and there's one more decision that we have to make. I said that those instructions were dependent on your microarchitecture. That is, using a specific instruction would make your code non-portable. There are two ways to solve this problem. You could do it statically. That is, you will produce different binaries for each microarchitecture. This is doable, but this will put a lot of stress on your release pipeline. We went with a different approach. That is, we are detecting at runtime dynamically the features supported by the CPU. You can see we have those configuration blocks. The first one is for x86 AVX, the other one x86 SSC. Then we have ARM, and at the bottom, this is our fallback implementation, the dot similarity one that was showing up in the flame graphs. Let's go a bit deeper and have a look at the dot similarity AVX. This is what SIMD code looks like. So first, it's pretty unsafe. Even internally, to make it work, you're going to have to rely on row pointer to load data. In that case, this is AVX2, I believe. We use 256 bits register. Now, the trick that you have to remember here is that we have a 256 bits register, and we're working with F32 float. That is, we're able to fit 8 floats into the register. And here the magic is that we're going to process the dot product 8 floats at the time. The for loop here goes through those two arrays and perform a multiplication addition with the fmadd. I won't go through the details because the code can be a bit tedious. And at the end, we do a sum. We have in that sum 256 register, we have 8 float that somehow we need to reduce, sum, and cast out an F32. This kind of code is not easy to write. You need a lot of knowledge, and I'm really happy we have someone that is very knowledgeable on our team, which makes this much easier. Oh, by the way, this is a simplified version. The real version is called .avx as well. You can find it in our code base. It doesn't fit on the slide, but if you want to go fast, sometimes you have to go dirty. Is it any good? Well, here we have a Criterion benchmark that compares our dot product function iterator base with the SIMD one. And we use, it's important to be precise here, the data set uses vectors with 1,000 dimension. So that's pretty large. And we see a 10x improvement. As we are processing floats 8 floats at a time, we could already expect 8x, and we get a little bit more because we're also making the addition a bit faster. When you see benchmarks like that, you're always very happy, but the question is always, how is this performing in an end-to-end system? Now we're going to see how SIMD impacts indexing and indexing benchmark. I took 100,000 vectors of dimension 500, and I've indexed those on my laptop. So let's say the absolute numbers here are not very interesting. It's done on my laptop, and I'm pretty sure I had other processes running at the same time. So we're building this HNSW index with our dot product, and we can compare the two results here. We can see that the dot iterator is above 300 seconds, and when using the SIMD version, we are under 100 seconds. So It's a really great gain. I mean, we basically changed, I don't know, 150 lines of code. You would really miss out not using SIMD for this use case. And interestingly, before using SIMD, we were using the OpenBlast project, which is kind of a reference in terms of speed for linear algebra operation. It's done in C and Fortran. And thanks to the work of the team in optimizing our SIMD operations, we now have similar performance with that project, which is really a great achievement. A bit about the architecture of the project. We said we have a collection that holds vectors. Internally, a collection is composed of several segments. And those segments are kind of created on demand as you add more points. Each segment is independent in terms of storage. We have inside a segment, we have the vector storage. We have the payload storage done independently. And those two are done, are persisted within RocksDB. We use the Rust RocksDB binding there. Concerning the HNSW index, we save it in a binary file that we handle ourselves. Those segments, they have a life cycle. They can be full. You need to create a new one. Still, you need to be able to delete things in there. So we have a couple of optimizers that are running in the back that are performing batch deletion, going through the tombstones, sometimes merging two segments together, and so on. Interestingly, when you create a collection, you have to make a choice. Do you want to use an in-memory approach, or do you want to use an memmap approach? That is, do you want to load all your vectors in memory, or you don't have enough memory? Maybe you want to use memmap. Concurrent programming. I think by now you understand that Qdrant is is inherently stateful. We have to juggle with segments, indexes, different storage, and it's quite complex. At the same time, we need to manage the concurrent access on this data. In Rust, you have, like, broadly speaking, two fashion of doing concurrent programming. Either you share data between threads via channel, which is a bit akin to the actor model, where the mutable state is enclosed within threads. Or you do thread synchronizing on a concurrency primitive such as mutex or RwLock. We use both flavor depending on the use case, but we had a lot more, let's say, fun and with the mutex and RwLock. So this is where I'm going to go a bit deeper. Before talking about the RwLock, the mutex protects a piece of data and enforce a single thread accessing it at a time, so it's very strict. If you want to have something less strict, you have the RwLock, which gives you several readers at a time or one writer. The beautiful thing about those API in Rust is that they enforced, the proper usage is enforced by the type system. Here on the right-hand side, this is an example that I shamelessly took from the standard library. You can see there is no unlock method. When you acquire a lock, there's no unlock to do. And this is a bit difficult to understand for people coming to Rust. What's happening here is that when you acquire a lock, if you do a lock.read, you get what's called a read guard. If you do a write, you get a write guard. And as long as you hold this guard, you are holding the lock. Either you need to drop the guard explicitly, or you wait for it to go out of scope to release your lock. The nice thing about this API as well is when you have a lock, a read lock, you can access the data because the read guard implements deref. And the same way, when you have a write guard, you can access the data and get an exclusive reference out of it because it implements deref mute. Those API are really nice. We use a lot of locks in our code base, but we use a lot of locks from Parking Lot, which is another crate that has like more concurrency primitive. They are generally faster and lighter. The problem with locks is, of course, deadlocks. Remember, deadlocks is threads waiting for each other. Here we have thread 1 that holds resource A, and thread 2 that holds resource B, and then they want to access the neighbor's lock, and they will stay like this forever. Another way it can happen is if you perform a double read lock on the same thread, because in Rust locks are not reentrant, you can run into this issue. I was talking a lot about locks, but you can get deadlocks also with channels. If you start playing around with channels with capacity and cycles, this is very dangerous as well. Those issues with deadlock, they're not caught by Rust, and this is sometimes surprising. People expect that all concurrency issues are magically taken care of by the Rust compiler, but this is not the case. This means fixing but avoiding those issues require discipline from yourself. There are several techniques. You could decide to acquire the locks in the same order on all the threads in the code base, or you, instead of reacquiring those locks all the time, you just pass the guards as arguments to your function. Luckily, there are some tips I can give you to help you, because we did have, I would say, a dozen deadlocks, and it's absolutely not fun to track. The first one is to use a runtime deadlock detector. This is a feature from Parking Lot. This is a build feature, so you need to enable it in your cargo toml file. We do it only for our CI build. So our CI build will check deadlocks. And it saved us one time here. We were able to find a deadlock in our cluster status. And when the deadlock happens, you have a really nice stack trace, and it's really helpful. So in my opinion, the deadlock detection is such a killer feature that it justifies using Parking Lot. If you want to go further than this, and you want to try some bleeding edge technology, you can try a static deadlock detector. So this is the project Logbud from Burt and Quinn, which analyzes your code and try to run some simulation to find potential issues in the interaction with the code. We discovered this project because the author just came on our GitHub issue tracker and said, you potentially have a double read lock in your proxy segment. And that was very nice of him. And we fixed it right away. You can use the project yourself. You need a bit of extra, let's say, Rust toolchain tooling, plus you need to compile it with nightly, but it's definitely doable. This project supports the standard mutex, RwLock, and Parking Lot as well. I recommend you have a look at it. Let's go distributed. Having a single node, you can really go a long way with Qdrant. First with Rust, then the SIMD stuff. On a single beefy node, I went myself with more than 30 million vectors, and it was very blazing fast. However, that's maybe not the architecture you want to go with on production. First, you want to stay available. If you have only a single machine, it goes down, you're gonna have a bad time. Also, when you scale, you want to scale on commodity machine. Scaling by hosting only really beefy machine gets very expensive. The way we did it in Qdrant is we have a classical shard replica architecture. When you create your collection, you say how many shards you want and how many replicas. It's pretty straightforward from a user perspective. We do not have leader shards for write. What we do is you send your request to anyone, and we'll figure out where the write should be executed. Any of the replicas can handle a write, and then this write is propagated to other replicas. By default, we do not have transactional operation on the vector. So if you need to support concurrent write on the same points, that's something you have to parameterize yourself by passing a little extra option. We will know that we need to serialize those writes. The way we do it, we had to synchronize some kind of cluster state and have a distributed collection topology. And to do so, we use the Raft consensus algorithm. Quick 101 on Raft. The Raft consensus algorithm enables you to have your node agree on a sequence of operation. This is called your log, and your log has entries, and you want this log to be replicated everywhere. Everyone needs to agree on what's on the log. It's critical. Once this log is replicated, you can execute it. It's a style that is called often the state machine replication. If you have the same state machine everywhere, if they run on the same data, you should have identical result. In Raft, there is a single leader that is elected. And the role of the leader is to receive the proposal for the new entries and send them to the followers. And once the follower act, I've replicated that thing, it tracks it. And when a majority of the followers has replicated an entry, the leader will commit it. And that says, I'm committing this means, follower, please process this entry. Now, it's a common misunderstanding with Raft. People seem to think that this is some kind of atomic, global, distributed consensus, but you will have basically lags, node lagging behind. So you need to be careful. If you start performing read on your follower, you most likely get stale read, and you have an eventually consistent system. In that case, you need to perform your reads on the leader. Using Raft in Rust, we decided to go with the Raft RS library. This was the most mature library we found at the time. It's definitely not easy to integrate in a code base. There's a complicated, dense to process the message, plus you have to implement your own persistence layer for the log. You have to be really careful there. We had some questions, but luckily the maintainers are very nice and very responsive, so kudos to them. Going in this kind of adventure when you debugging can be very difficult. Make sure you have good logs and good tests. All right, time to wrap it up here. A couple of takeaways. I hope I was able to demystify vector search engine for you, that you know now when to reach for it, what kind of use case it supports. We went through a couple of new indexing schemes to support approximate nearest neighbor and the specific implementation of HNSW. Also, now you know you can apply SIMD to your bottlenecks. If it's possible, you should do it. Here we're doing a lot of float F32 business, but even if you do backend applications, you can parse JSON with SIMD JSON. Just give it a try. Modern hardware is really fantastic. Fearless concurrency in Rust, sure, but except for deadlocks. And this is the responsibility of the developer to make sure those does not happen. Distributed systems are hard. That's not very new, but I had to put it. And basically, this whole presentation is, I guess, another data point in favor of Rust for building concurrent, highly distributed systems. I will leave you with a couple of links. We have first, of course, our GitHub repo, then our documentation, a couple of benchmarks where we see how we fare against other engines, our blog where we push articles about new features and new trend. For instance, now you can start using semantic search for code search. It's very interesting stuff. And the best way to connect with us and the community is via Discord. That's all for me.